In the early years of the Cold War, as NATO defense planners assessed the logistical vulnerabilities exposed by the Berlin airlift and the rapid mechanization of post-war armed forces, they concluded that fuel, more than ammunition or manpower, would be the pacing commodity in any large-scale conflict on the Central European front, because jet aircraft, armored divisions, motorized infantry formations, and tactical support vehicles all consumed fuel at rates that could not be sustained through road tanker convoys alone under conditions of interdiction, congestion, and potential infrastructure destruction. And from this assessment emerged the concept that would become the Central Europe Pipeline System, or CEPS, a permanently constructed multinational fuel distribution network embedded across Western Europe and specifically engineered not merely for peacetime supply, but for wartime resilience, redundancy, and surge throughput, aligned with NATO's defense plans. And the origins of CEPS can be traced to early 1950s planning conferences within NATO's infrastructure committees, where representatives from the United States, United Kingdom, France, Belgium, the Netherlands, Luxembourg, and West Germany debated how to construct a fuel delivery architecture capable of sustaining continuous air operations and armored maneuver without relying on vulnerable surface transport. And these deliberations occurred in parallel with the establishment of NATO's integrated military command under Supreme Headquarters Allied Powers Europe, which emphasized that logistics systems must be multinational, standardized, and protected against single-point failure, and therefore CEPS was conceived not as a single pipeline, but as a network of interconnected trunk lines, pumping stations, storage depots, and lateral distribution branches extending from coastal refineries and ports through Belgium and the Netherlands into France and West Germany, forming a fuel backbone that could deliver aviation kerosene, diesel, and other refined products directly to airbases and military storage sites without the need for exposed truck convoys. And construction began in phases during the 1950s under the NATO infrastructure program, with participating nations financing segments on their territory according to agreed cost-sharing formulas. And engineers designed trunk lines with sufficient diameter to sustain flow rates measured in hundreds of cubic meters per hour, calibrated against projected wartime sortie generation rates for tactical air forces stationed in Western Europe, as well as fuel consumption tables for armored corps expected to defend the central region. And from the outset, planners incorporated redundancy into the system, ensuring that multiple pipeline branches could feed major air bases such as Ramstein, Spangdahlem, and Buchel in West Germany, so that if one segment were severed by sabotage or air attack, alternate routing could preserve continuous supply, and hardened storage sites were constructed at strategic intervals along the network, often concealed or protected by earth berms and reinforced concrete to mitigate blast effects. With total storage capacity measured in millions of liters sufficient to sustain several days of high-intensity operations without immediate replenishment from refineries. And dispersal strategy was central to the design, as NATO planners recognized that concentrated fuel farms presented lucrative targets, prompting the distribution of storage tanks across multiple sites linked by underground pipelines rather than single centralized depots, thereby reducing vulnerability to catastrophic loss. And by the 1960s, CEPS had expanded into a dense lattice of more than 5,000 kilometers of pipeline spanning key NATO territories, integrating with port facilities capable of receiving tanker ships and pumping refined fuel directly into the network, effectively transforming Western Europe into a fuel grid where coastal import points, inland storage, and forward distribution were fused into a single controlled system overseen by NATO's Central Europe Pipeline Management Organization. and throughout successive decades of the Cold War, CEPS was continuously upgraded to increase throughput, enhance security, and align with evolving NATO force posture, embedding fuel redundancy directly into the geography of the alliance's most vulnerable theater, and ensuring that in the event of Warsaw Pact attack, aircraft and armored formations in Central Europe would not be immobilized by fuel disruption during the decisive opening phase of conflict. As construction of the Central Europe pipeline system accelerated through the mid to late 1950s, NATO planners treated it not as a commercial energy network adapted for military use, but as a purpose-built wartime sustainment architecture engineered around operational fuel consumption models derived from projected sortie rates and armored maneuver doctrine, and, therefore, technical design decisions were anchored in quantitative planning assumptions, including expected daily aviation fuel demand per tactical air wing, diesel requirements per armored division during sustained defensive operations, and reserve margins measured in days of supply to cushion against refinery disruption or port interdiction, and trunk lines were constructed with diameters sufficient to sustain high volume flow rates, often exceeding several hundred cubic meters per hour under surge pumping conditions, while pumping stations were spaced at calculated intervals to maintain pressure continuity across long-distance segments stretching from North Sea and Channel ports through Belgium and the Netherlands into West Germany, and these pumping facilities were designed with backup power generation capacity to ensure uninterrupted operation in the event of grid disruption, reflecting the expectation that electrical infrastructure might be targeted in wartime. And storage. Depots were deliberately dispersed rather than centralized, with multiple tank farms positioned along lateral branches feeding key air bases and garrison areas, each equipped with fire suppression systems, reinforced berming, and in some cases partial burial, to reduce vulnerability to blast and fragmentation. And the dispersal strategy extended to the routing of pipeline segments themselves, which often followed indirect alignments to avoid predictable choke points and were buried underground to reduce susceptibility to air attack or sabotage. And integration with port facilities was equally central to the architecture, as coastal terminals in Rotterdam, Antwerp, and other key entry points were fitted with high-capacity pumping infrastructure, capable of transferring fuel from tanker vessels directly into CEPS trunk lines without intermediate truck transport, thereby eliminating surface exposure and accelerating replenishment cycles, and the multinational governance framework overseeing. CEPS required harmonization of fuel standards across participating nations to ensure that aviation kerosene and diesel products met NATO interoperability specifications, preventing compatibility issues that could degrade aircraft performance or engine reliability. And as West Germany joined NATO in 1955, the expansion of CEPS eastward intensified, with additional trunk segments laid to support the growing concentration of U.S., British, and German forces in the Federal Republic, embedding the fuel network into the operational geography of the Central Front. And by the early 1960s, CEPS had matured into an interconnected grid spanning several thousand kilometers, linking refineries, ports, storage farms, and air bases into a unified distribution system whose resilience was reinforced by looped routing, allowing bidirectional flow, so that if one segment were compromised, fuel could be rerouted along alternate paths, and NATO exercises periodically tested surge pumping capacity by simulating elevated sortie generation rates and measuring whether flow volumes could sustain increased consumption without pressure loss or bottleneck at transfer nodes, generating empirical data that informed incremental upgrades to pump horsepower, valve systems, and storage capacity. And thus, by the mid-Cold War period, CEPS represented a hardened, redundant, and technically sophisticated infrastructure designed explicitly for war, embedding fuel security into NATO's defense posture and ensuring that air power and mechanized formations in Central Europe would retain operational mobility even under sustained interdiction and infrastructure attack scenarios envisioned during superpower confrontation. By the late 1960s and into the 1970s, as NATO force posture in Central Europe stabilized around a forward defense concept anchored in West Germany, the Central Europe pipeline system underwent systematic expansion and hardening to match the scale and density of Allied air and ground formations stationed along the inner German border, because fuel demand projections increased in parallel with the modernization of tactical aircraft fleets and the mechanization of armored units, and NATO logistics planners recalculated required throughput based on updated sortie generation assumptions, including higher daily flight rates for tactical air wings equipped with supersonic aircraft and increased diesel consumption for heavier main battle tanks entering service. And these recalculations led to reinforcement of trunk lines with higher capacity pumps, capable of sustaining elevated pressure under surge conditions, ensuring that flow rates measured in cubic meters per hour could be increased during crisis without structural stress on pipeline segments, and additional lateral branches were constructed to connect newly established or expanded airbases, embedding CEPS more deeply into the operational footprint of US, British, Belgian, Dutch, and West German forces, while hardened storage capacity was increased at selected inland depots, often through the addition of partially buried or berm-protected tanks designed to reduce thermal and blast vulnerability. And redundancy was further enhanced by constructing looped segments that allowed fuel to circulate around damaged nodes, permitting bidirectional routing if a pumping station or trunkline section was rendered inoperable. And NATO engineers integrated automatic shutoff valves and sectional isolation mechanisms at calculated intervals, enabling rapid containment of leaks or sabotage attempts without disabling the entire network, reflecting an operational assumption that wartime disruption attempts would target critical junctions, and governance mechanisms under the Central Europe Pipeline Management Organization were refined to coordinate multinational maintenance schedules, ensure standardized quality control of fuel entering the network, and manage shared financing for upgrades, thereby preserving interoperability across national boundaries. And regular NATO exercises included simulated surge demand scenarios in which airbase fuel draw was elevated to match projected combat sortie rates, allowing planners to measure pressure stability, pumping reliability, and depot depletion curves against modeled wartime requirements. And these empirical tests confirmed that CEPS could sustain several days of high-intensity operations before inland storage required replenishment from coastal import terminals, reinforcing confidence that fuel would not become the limiting factor during the decisive opening phase of a Warsaw Pact assault. And by the end of the 1970s, CEPS had evolved into a multi-layered, hardened distribution grid exceeding 5,000 kilometers in length, characterized by redundant routing, dispersed storage, and integrated port connections, constituting a critical structural component of NATO's Central European defense architecture, designed explicitly to preserve operational mobility under the most demanding conditions of superpower confrontation. As NATO doctrine evolved in the late 1970s and early 1980s toward a more dynamic concept of defense, incorporating deep strike, countermaneuver, and sustained high sortie rates under the air-land battle framework, the Central Europe pipeline system was reassessed not merely for baseline throughput, but for its ability to sustain elevated fuel demand under prolonged high-intensity operations, because new generation tactical aircraft, increased armored density, and expanded logistical mobility requirements significantly raised projected daily fuel consumption curves, prompting NATO infrastructure committees to commission updated flow modeling that recalculated trunk line capacity against worst-case operational tempo scenarios. And these analyses resulted in selective reinforcement of pumping stations with higher horsepower units capable of increasing flow velocity without exceeding pipeline pressure tolerances, as well as modernization of control systems to allow more precise monitoring of pressure, differentials, flow rate, and valve status across long-distance segments, thereby reducing response time to leaks or sabotage attempts. And hardened storage strategy was further refined through the expansion of underground or partially buried tank farms near critical airbases and logistics hubs, with storage capacity at certain nodes calibrated to provide several days of autonomous sustainment, measured in millions of liters, ensuring that temporary disruption of coastal import terminals would not immediately degrade sortie generation, and dispersal remained central to survivability planning, as additional lateral branches were constructed to reduce dependence on single supply corridors, while looped routing allowed fuel to bypass damaged nodes by reversing flow direction, a capability tested periodically during NATO exercises in which segments were isolated to simulate interdiction, confirming that alternate pathways could maintain supply continuity without significant pressure loss, and integration with port facilities was strengthened through modernization of pumping infrastructure at major entry points such as Rotterdam and Antwerp, increasing transfer rates from tanker vessels directly into CEPS trunk lines and minimizing dwell time at coastal terminals, thereby accelerating replenishment cycles during surge conditions. And multinational coordination mechanisms were formalized further to ensure synchronized maintenance across national boundaries, common fuel specification compliance, and standardized emergency response procedures, embedding CEPS within NATO's broader command and control framework. And throughout this period, intelligence assessments acknowledged that CEPS constituted a hardened logistical backbone underpinning NATO air power in Central Europe, because its buried pipelines, dispersed storage, and redundant routing reduced vulnerability relative to surface tanker, convoys, and by the mid-1980s, the system had matured into a technologically upgraded, resilient network capable of sustaining elevated fuel demand for tactical aviation and mechanized formations under conditions approximating sustained conventional conflict, reinforcing NATO's confidence that fuel supply would not become the critical bottleneck during the decisive early phase of a Central European war scenario. By the mid to late 1980s, as NATO conducted increasingly sophisticated reinforcement and readiness exercises across the Central region, the Central Europe pipeline system was treated as a fully operational warfighting enabler, whose performance had to align precisely with projected sortie generation curves and armored maneuver tempo under the most demanding contingency scenarios. And therefore, fuel consumption modeling was integrated directly into NATO's operational planning tools, linking daily aircraft sortie rates, tank battalion movement projections, and reserve stock, depletion timelines to measured pipeline flow capacity and inland storage volume. And planners calculated that tactical air forces operating at surge levels could consume millions of liters of aviation fuel per day across the Central Front, while armored corps defending along the inter-German border would require continuous diesel transfer at rates measured in hundreds of thousands of liters per division per 24-hour cycle. And CEPS trunk lines were evaluated to ensure that sustained pumping under these elevated conditions would not degrade pressure stability or exceed mechanical tolerances, prompting periodic upgrades to pump assemblies, control valves, and remote monitoring systems capable of transmitting real-time flow data to centralized management centers. And hardened storage strategy was further emphasized through selective reinforcement of tank farm protection, including additional berming improved fire suppression systems, and enhanced access control to mitigate sabotage risk, while dispersal logic ensured that no single storage site represented a disproportionate percentage of total inland reserve capacity, and looped routing capability was exercised in simulated disruption drills, isolating selected segments to confirm that fuel could be rerouted through alternate pathways without significant throughput reduction, thereby validating redundancy assumptions embedded in war plans. And port integration remained critical to sustained operations beyond initial stockpile depth, as coastal pumping facilities were tested for their ability to receive sequential tanker shipments and inject refined fuel directly into CEPS at rates synchronized with inland consumption curves, minimizing vulnerability to port congestion or tanker queuing, and multinational governance under the Central Europe Pipeline Management Organization coordinated these technical upgrades and ensured harmonized maintenance standards across participating nations, reinforcing the system's interoperability and reliability. And by the final years of the Cold War, CEPS had become a deeply embedded, technologically modernized, and empirically tested fuel distribution grid whose buried pipelines, redundant routing, hardened storage, and synchronized port integration provided NATO with a resilient energy backbone calibrated specifically to sustain high-intensity air and ground operations on the Central European battlefield during the decisive opening phase of a potential Warsaw Pact offensive. As NATO intelligence assessments in the late 1980s continued to evaluate Warsaw Pact operational capabilities, fuel sustainability remained central to alliance defensive credibility, and the Central Europe pipeline system was increasingly analyzed not only as infrastructure, but as a strategic deterrent multiplier, because its existence fundamentally altered the calculus of sustained air operations and mechanized maneuver on the Central Front, and planners understood that in the absence of a hardened, redundant fuel grid, tactical air forces would be forced to rely heavily on road tanker resupply, vulnerable to interdiction, congestion, and infrastructure degradation, dramatically constraining sortie generation rates. And therefore, CEPS was integrated into readiness reporting systems, with participating nations required to certify pipeline integrity, pumping station operability, and storage reserve levels at regular intervals, ensuring that surge capacity measured in cubic meters per hour and inland stockpile volume measured in millions of liters remained aligned with updated war plan assumptions, and redundancy modeling incorporated hypothetical scenarios in which selected trunk segments or pumping stations were rendered inoperable, testing the system's ability to sustain continuous supply through alternate loops without exceeding pressure limits or creating localized shortages at high-demand airbases. And these exercises confirmed that bidirectional flow capability and distributed storage provided sufficient elasticity to absorb moderate disruption while maintaining operational tempo, and dispersal strategy continued to guide storage placement, with inland tank farms intentionally separated geographically to prevent single-strike depletion of regional reserves, while automatic isolation valves segmented the network into controllable sections, enabling rapid containment of leaks or sabotage without halting flow across the broader grid, and integration with port terminals was periodically stress-tested to ensure that tanker discharge rates could match inland drawdown curves during extended operations, reinforcing the link between maritime import capacity and sustained pipeline throughput. And multinational oversight mechanisms ensured standardized fuel quality control across the network, preserving aircraft engine reliability and interoperability among allied air forces drawing from shared infrastructure. And by 1990, CEPS stood as a mature, deeply embedded component of NATO's defense architecture. Its buried pipelines, hardened storage, redundant routing, and synchronized governance, forming a resilient energy backbone capable of sustaining elevated fuel demand during the critical opening phase of a Central European conflict, illustrating how infrastructure deliberately engineered for war had become inseparable from the alliance's operational planning and deterrence posture during the final chapter of the Cold War. When viewed across the full arc of the Cold War, the Central Europe pipeline system represents one of the most strategically consequential infrastructure projects undertaken by NATO, because it translated the abstract requirement for sustained fuel supply into a permanently embedded multinational distribution grid engineered specifically for wartime resilience. And from its early 1950s, origins in infrastructure planning committees responding to lessons of fuel vulnerability through successive decades of expansion, hardening, and modernization, CEPS evolved into a network exceeding 5,000 kilometers of buried pipeline linking coastal import terminals, inland storage depots, pumping stations, and forward airbases across Belgium, the Netherlands, France, Luxembourg, and West Germany, and every element of its design reflected operational calculations derived from projected sortie generation rates and armored fuel consumption models, including trunk diameters sized for high-volume surge flow, pumping stations equipped with backup power to maintain pressure under grid disruption, sectional isolation valves to contain damage without disabling the entire system, looped routing, permitting bidirectional supply around compromised nodes, and hardened, dispersed storage farms capable of sustaining several days of high-intensity operations, measured in millions of liters before requiring replenishment from tanker vessels at North Sea and Channel ports, and multinational governance, under NATO oversight, ensured standardized fuel specifications, synchronized maintenance cycles, and coordinated emergency procedures, embedding CEPS within the alliance's broader command and control architecture, while periodic exercises validated throughput capacity, pressure stability, and rerouting resilience under simulated disruption, confirming that the network could sustain elevated demand from tactical aviation and mechanized forces during the decisive early phase of a Central European conflict, and by the final years of superpower confrontation, CEPS stood not merely as logistical infrastructure, but as a structural guarantor of operational mobility, ensuring that aircraft would not be grounded and armored formations would not stall for lack of fuel, even under conditions of interdiction and infrastructure attack envisioned in Warsaw Pact war planning, illustrating how NATO transformed vulnerability into engineered redundancy by fusing buried pipelines, hardened storage, dispersal strategy, and synchronized multinational management into a cohesive fuel backbone built explicitly for war in the heart of Europe. In its final Cold War configuration, the Central Europe pipeline system embodied the principle that modern, mechanized warfare is ultimately constrained by energy flow, and NATO's response to that constraint was to embed fuel security directly into the geography of Western Europe through a hardened, redundant, and multinationally governed pipeline architecture designed explicitly for sustained conflict. And this architecture fused coastal tanker reception terminals, high-capacity trunk lines, looped routing segments, sectional isolation valves, backup-powered pumping stations, and geographically dispersed storage farms into a single controllable grid, capable of sustaining continuous aviation and ground fuel supply under projected high-intensity conditions, with inland reserves calibrated in millions of liters and flow rates measured in hundreds of cubic meters per hour to match modeled sortie generation and armored maneuver demand during the critical opening days of a Central European war scenario, and redundancy ensured that damage to one segment could be mitigated through alternate pathways without catastrophic system failure, while hardened and partially buried storage reduced vulnerability to blast and fragmentation, and multinational oversight harmonized fuel specifications, maintenance standards, and emergency response protocols across national boundaries, guaranteeing interoperability among allied forces drawing from shared infrastructure, and repeated surge and disruption exercises validated that CEPS could maintain pressure stability and throughput even when segments were isolated, confirming that fuel distribution would not collapse under moderate interdiction. And by 1991, although geopolitical transformation was rendering large-scale conflict in Central Europe increasingly unlikely, the pipeline grid remained, intact as a testament to decades of deliberate engineering aligned with NATO operational doctrine, demonstrating how the alliance transformed fuel from a logistical vulnerability into a strategic asset by constructing an underground energy backbone purpose-built to sustain high-tempo air and mechanized operations during the decisive phase of Cold War confrontation.